chapter 10, which is the gases. We're going to do 10 and then we'll go back to 5. So let's talk about gases. Now, remember, this is the only chapter where we're dealing with gases. Remember, they're widely spaced and they're disordered. And remember, if I could spell disordered. And they're in constant motion. So they're different from the other ones, which are called condensed phase. And those are both solids and liquids. Liquids are still closely spaced. And they are disordered particles. But they have very limited motion, because where gases will go all over the entire container, liquids only stay in the bottom. And solids, on the other hand, are closely packed or spaced, and they are ordered. Now, there is some in fixed positions. Now, I'm not saying that there is not any motion and very limited motion, because they will vibrate in space. So what I compare them to is, if you were in a classroom and we turned off the gravity and you could free float all over the room, then you would be a gas. If we were placed off, instead of having chairs behind the tables, we had benches and you could slide back and forth, you'd be a liquid. By putting chairs in there where you can't move the chairs other than to rotate in place, you are a solid. Okay? So this entire chapter is going to deal with gases. Now, 3 major properties of gases that solids don't have are compressibility. This is where the relative volume change is in response to pressure. So if you think about this when you're dealing with certain things like your brakes in your car, if you press down, you want to hit a liquid which will press down as well on the brake pad. If you have air in the line, that's where you press down and nothing happens, because you've got air, which is a gas, which is compressible. Okay, expandability, gases will expand to fill the container. And that is not something that solids or liquids do. They don't expand. They just kind of sit there. Okay. Now, the other important factor is the volumes occupied by the same amount of substance in gas form is much, much, much greater than in liquid or solid form. And this is why over here in this corner, and if you were looking at a real PowerPoint slide, those kernels would be popping. That's why popcorn pops. And that is why there's this whole thing about storing it in the freezer, not storing it in the freezer, etc. Because what happens is there's a certain amount of water in each kernel, and the kernel has to be tight enough to hold the water in place. So when you microwave it or heat it on the stove, you heat up the water and convert it from liquid or solid if it's frozen to gas. So that's why you get the sudden explosions of the popcorn. Okay, so we're talking about volume and pressure a lot. So pressure is force over area. The amount of pressure felt is a function of both the force and the area over which the force is. Now, this is actually pretty critical, because if you think about it, and we live in the South, okay? If you've been in the North in the snow, walking on snow is hard. But if you strap snowshoes on, it's easy to walk on snow. Why? You haven't changed the force, But what you've done is you've increased the pressure. The area. So by increasing the area, the pressure has dropped. And so you don't sink through the snow. Okay? So this is critical, and we'll talk about it with respect to pressure, atmospheres, etc. Okay? In SI, the force is expressed in newtons in the area in meters squared, so pressure is Newton per meter squared. We don't use that form in chemistry, but if you're taking physics, you're like, wait, we've done this. Yes, it's pretty much the same thing, except we use different units. Okay, now, this is an interesting slide because everybody always asks, why do I need to know this? Well, pressure, sound transfers via the movement of air, which causes a pressure change. So the pressure goes in and it hits your tympanic membrane, your eardrum, and it causes a difference. And then that's what your body recognizes as differences in sound, etc. There are little hairs in there and all kinds of things. You can they don't really have the hairs in there, but that, etc. So the bottom line is this is why if you break your eardrum, you have a problem with sound, or if you mess up the hairs or anything in there by experiencing too loud of a noise for too long, then you kind of go deaf. Okay, here's atmospheric pressure. Atmospheric pressure is basically, if you imagine a really long column way up, the gravitational force. So the atmospheric pressure is the pressure of the atmosphere pushing down on the earth. And so the interesting part of that, and some of the weather apps will show this, is they'll talk about highs and low pressures. And what that does is that controls the weather. If you have a high pressure, its net effect is going to push weather away from it. Low pressure, it draws it in. Weather usually being clouds, which means you get rain. Okay, more about that when we get to hurricanes because they're a lot of fun. All right, so if you're using a barometer, you're measuring the pressure at sea level on a sunny day, and you use a column of mercury, and it's going to balance the pressure by pushing on the pull of mercury down below. Now, this was originally how it's done. Now we know that mercury is bad. Well, mercury's really not bad. Just don't eat it and don't, wash your hands in it. But it's cool otherwise, and good barometers still use mercury because it's really the best thing. And the pressure is a function of the height of the column. Okay? So you can do this with an open end or a closed end. If you're measuring a particular gas, we call that a manometer. And so you might see that referenced in problems. Okay, so we're going to talk about units of atmosphere. Now, the one you have to memorize is an atmosphere of 760 millimeters of mercury. That's exact. Remember what exact means? That means that's infinite significant figures. And you're going to use that so much that you're going to know it. I'd go ahead and memorize it. Same thing with this one here. Basically, what this says is a torr is the same thing as a millimeter of mercury. Okay. Now, these other ones you don't have to memorize. These will be given to you. One atmosphere is 1,001.325 pascals or 101.325 kPas, kilopascals. Atmosphere inches to bars in atmospheres to pounds per square inch. This is what we use in the United States. The interesting thing is, why do you have to know all these units? Well, if you're on the water, you're in the Navy, you're a Marine, Coast Guard, Merchant Marine, etc. Bars are usually used by people who are associated with the water. KPAs are used by a variety of other people. Weather people on the TV use inches of mercury. Okay, so bottom line is why? Well, I really don't know why different ones use different things. but you need to be able to arrange all of them. Okay, so for example, the TV weather person says the barometric pressure is 30.1 inches of mercury. What is this pressure in atmospheres, kPAs, and psi's? So if we're doing it in atmospheres, we're going to start with 30.1 inches. Now, you may know that 29.921 inches is equal to 1 atmosphere, which means it's 1.00598 atmospheres. Now on this one, this is the first number is 3, the second number is 4 significant figures. So you report this in 3.01 atmospheres would be your final number. Or I can never remember that, a conversion 29 to 92. I'm not sure if I give it to you or not. I'll check. 3.1 inches, 1 inch, 1 inch is 2.54 centimeters, and there are 1 centimeters per 10 millimeters, and there are 760 millimeters per 1 atmosphere. Now I ran out of room here, but you can see this. So the net effect is you get 1.005973, which again gives you 1.01 atmospheres. Now, does it matter which one you use? No. Within significant figures, they're the same, so it's not a big deal. All right. Now, the second one is in kPa. So again, we're going to start with 30.1 inches. I'm going to stick with my 2.54 centimeters is 1 inch, only because, A, it's more steps. B, I like it. And remember, they're in 2.54 centimeters per inch. That's exact, so that's infinitely many, and then it's all metric. So I like it also because it's going to keep me significant figures. Millimeters happens to be of mercury is 1 atmosphere, and we're going for kPa, so 1 atmosphere is 101.325 kPAs. So we end up with 101.930 kPAs. We're dealing with 3 significant figures, so it's 102 kPAs. Now notice that we've got 101 atmospheres, but now we got 102 kPAs, so it's a rounding. And the third one is PSI, which is pounds per square inch. So we're going to start with our inches, and we know that, and I'll use the other one, 29.92 inches per 1 atmosphere. And 1 atmosphere is 14.6959 psi. So I end up with 14.738 psi. No, I left off an 8. 14.7838 psi. Again, 3 significant figures, so 14.8 psi. So here, notice we've got the exact same temperature. We're getting 101 atmospheres, 102 kPAs, and 14.8 psi's. Okay. So why is this important? Well, I'm always amused because in hurricane season, and because of the in 2020, they're talking that there's this big plume of dust coming over from the Sahara Desert, which is actually not unusual. But the thing about it is when that happens, one of the experts says that it lowers the chances of hurricanes. So, in theory, we get a lot of dust, we have less hurricanes. But if we have a hurricane, and they send the hurricane hunters out, then suddenly, instead of using inches, they start using millibars. Now, why do they do this? Other than to make you crazy. Okay, the reason they do this is the hurricane hunters tend to be Air Force. And the Air Force uses millibars. And why do we care? Well, with hurricanes are more intense the lower the pressure in the eye of the hurricane. Okay, so hurricanes with a high pressure are strong, maybe strong, but they're not usually that strong. They're, you know, fours and fives usually. When you get into really low pressures, you get into the ones and the twos. Okay, so the second strongest was Camille. I think the first one was Katrina, and there's another one that is kind of unnamed because it was before they started naming stuff. So when they start talking about hurricanes, then they suddenly start using millibars. Okay. And so this one was Florence, which we had a couple years ago here. And second strongest was Camille. And so what is the pressure in millibars? Okay. In atmospheres, etc. So we're going to do Florence. So we want to know what it is in atmospheres. So we're going to start with 958 millibars. Now remember, a millibar is 1,000th of a bar. So millibars you use, it's just the milli. So there are 1,000 millibars in one bar. Sounds like you're hanging out with liquor. Okay, one atmosphere is 1.01325 bars. Now, if you'll remember, you're like, wait, I've seen that number before. Yes, 101.325 is a kPa, and 1,325 is a Pascal. So you're like, wait, really? They're just using different versions of the same number. Yeah, it kind of works out that way. So we have 0.9454 atmospheres for 7 atmospheres. We're using 3 significant figures, so it's 945 atmospheres. Well, one atmosphere, if you think about it, dropping that much is pretty impressive. So if we're doing millimeters of mercury, we'll start with 958 millibars. And let's convert it back to bars. And if you notice, I'm not using what I did before, only because in case I've plugged in a number wrong, then I'm not using the same bad number. So 1 bar is 750.06168 atmospheres. Now remember, 1 atmosphere is 760. No, that's not atmospheres, millimeters of mercury. I was thinking ahead. Shouldn't do that. So remember, 1 atmosphere is 760 millimeters, but 1 bar is only 750. So what we end up with 718.55989 millimeters of mercury, or remember we can call that torr. So if again for 3 significant figures, we're 700. Whoops, we're not that. We're 719 torr, or millimeters of mercury. So if you think about it, if you go from 1 atmosphere to 0.945, that doesn't seem that impressive. But if you go from 760 to 719, that's 40 millimeters. So it drops. So the thing about it is that when you're talking about pressures in hurricanes, you need to be talking about it with respect to apples to apples. So the thing about it is as I said, suddenly in the hurricane season, they start using millibars and bars and stuff, and you're like, wait, what happened to the inches? So if some of y'all are amateur meteorologists or amateur hurricane hunters and track this, then you need to know the conversions back and forth. Okay? Now, the biggest take-home message to this is you're not stupid. But most things on the news, TV, whatever, treat you as if you are, because they may not want you to know what the real numbers are or confuse you. So annoying people like me sit there and recalculate and go, oh, you're talking about this much of a pressure drop. And other people are like going, but they said, it was what. Okay, as scientists or future scientists, always check numbers, etc. Okay, so this gets us through pressure. In the next part, we will start working on individual gas laws, and we'll walk you through that.